All right, 3.7, optimization. This is another application of derivatives. That kind of should make sense. Chapter 3 was all about applications of derivatives. And so this one is going to be looking for an optimal value for something. So you're wanting to make something as big or as small as possible. And so you can imagine things that you like to do that with, right? So like if you wanted to make your paycheck as big as possible, that's an optimization kind of question. Maybe not calculus related, but that's what it is. It's optimizing something. Or if you wanted to make something as small as possible, right? Like the minimum amount of time I have to put in to a class in order to get a C in the class or a B in the class or an A in a class, right? You're trying to optimize your time schedule to make sure that you're getting the most bang for your buck. Those are optimization kind of questions. We're going to take a look at some calculus related ones. And here are some general guidelines for optimization. It is often helpful to make a visual. A lot of the ones, maybe everything that we're going to do is going to have some kind of a visual we can make a sketch of. Identifying what you know and what you need to find. The quantities you know and the quantities you need to find. 3 is writing any applicable equations, so things that relate what you know to what you need to find. Figuring out what it is you're trying to optimize, right? Are we trying to optimize the area? Are we trying to optimize our profit? Those kinds of things. And then rewriting that equation if need be in terms of only one variable. Sometimes that's something we have to do, sometimes it's not. Step 4 and step 5 are the calculus steps. So 1 through 3 is all algebra actual stuff, right? It actually is. 4 and 5 is where the calculus comes into play. And so in chapter 3, we looked at finding maximum and minimum values of things. So using the calculus on step 5 generally means finding a derivative, setting it equal to 0, and solving. Okay, so that's what step 5 is all about. Step 4, where it determines the maximum minimum allowable values, has to do with the constraints of the problem. So, for example, if you're trying to fence in, a yard, you only have so much feet of fencing. You cannot have infinite fencing. So there's a cap on like the area. There's a cap on the length or the width or the perimeter. Whatever it is that you're sort of have a maximum or minimum value of for it to make sense contextually. You can't have negative numbers for the most part in optimization problems because they don't make sense because we're actually looking at a physical image of something, so I can't have negative feet of fencing. So there's generally speaking a maximum and a minimum reasonable value that we could be using, and that's what step 4 is, and then step 5 is actually finding derivatives, setting them equal to 0, and so forth, okay? So we're going to do one that, to be perfectly honest, can be done with algebra, okay? But I want to sort of show you how it can be done with calculus, and it's actually a little bit cleaner, which should come as no surprise. The more tools you have to do things, it's usually easier because you've built up to the point where you can do that. So we're going to take a look at a 3-sided fence. It's going to be built next to a straight section of river, which forms the 4th side of a rectangular region. The enclosed area is equal to 1,800 square feet, and we want to find the minimum perimeter and dimensions of the corresponding enclosure. So what did step 1 say that I should do first? Make a visual. This has a very good picture of what's going on. We got a river. And we're going to build a fence that's 3-sided along the river. And prior experience tells you that when you work with fences, unless there's a reason not to, you're generally talking about something that's a rectangular shape. So this seems reasonable, right? It tells us that we know what the area is. Okay, so let's just jot that down. I know that my area is 1,800 square feet. Okay, so I'm at the point where I'm looking at part 2, where it says identify quantities known and those to be found. I know the area, and I'm asked to find the perimeter, right? It says, what's the perimeter? In other words, how much fence do I have to buy, right? That's the practical application, right? If I'm actually trying to create this thing and I want it to have 1,800 square feet of area, I need to figure out how much fencing I have to buy. Right? This is not altogether unlike when I'm going to go and fill my gardens with my flowers this weekend, right? I got to figure out how much I'm going to fill into my flower bed, right? To optimize my space, the distance between the plants, those kinds of things. So it's the perimeter or the fencing this time that we're trying to buy and we're trying to find how much or the minimum amount of fencing I would need to buy. Okay, so in terms of my image, right, this rectangle over here, that's a 3-sided rectangle because I don't have to fence along the river according to the problem. What are some variables that I can use that you've seen used before, or ones that you just want to use anyway, for the side lengths of my fence? Base and height. Okay, so how about we do this one is base and this one is height? Does that sound okay? All right. What's the top going to be? That's the base again, right? That's what you know, previous experience about rectangles, is that the sides opposite each other are equal in length. Everybody good? I know my image doesn't look like it is because my river is going sideways, all right? So we're assuming that it's a straight river. It says a straight section of river. My image, my picture doesn't quite mimic that very well, but you can pretend like it is, right? Yours probably looks a little bit better than mine. All right, so what is the perimeter of this object? Close. 2 base plus the height, right? I have to add the 3 pieces together. My perimeter is the 3 sides of the shape all added together. So, and that is a B, although it kind of looks like a 6. So I'm going to write that again. Make that look a little clearer. All right, the other quantity that's listed here has to do with area. And I mean, I know the area, specifically that it's 1,800 square feet. But if I were just looking at the shape, what's the area of this shape that's been given here? This isn't a trick question, please. Base times height, thank you. We're not trying to trick anything. It's just base times height. So I have a relationship between the base and the height and the 1,800, and I'm trying to establish something about the base and the height with the perimeter. Does that make sense to everyone? So let's go back to our list of sort of guidelines. We've done step 1, we made our visual. We've done step 2, we've identified what we know and what we need to find. Step 3, we have created some equations and we've identified what we want to optimize. What was it that we're trying to optimize over here? The minimum perimeter. So it's the perimeter right here that I'm wanting to optimize, right? So this is what I'm wanting to optimize. I'll just write it in. I'm wanting to optimize my perimeter. And the last part of step 3 says that I want to write the equation, that is the optimization equation, in terms of only one variable. So when it talks about only one variable, it doesn't mean that I'm going to take this and turn it into one variable as opposed to sort of 3. It means the right-hand side needs to have only one variable. The left-hand side's perimeter, that's fine. But the right-hand side right now has base and height in it. And I need to replace one of them to be in terms of the other. Any idea what I might need to use in order to replace either the B or the H with something that we know more about? Yeah, okay, so the area function, just like Caleb mentions, has a relationship between the base and the height and the 1,800 square feet. So if I write this more concisely, this is saying that 1,800 equals base times height. Whoops, that's funny looking H. Let's try that again. Okay, so I would need to solve, and it doesn't matter which ones, you guys can pick for me. Do we want to solve that equation for base or for height? Somebody pick one. Base, thank you. So if I solve this for base, then I find that the base is equal to 1,800 divided by the height. Right? And what that means, let me move this up just a little bit so I have a little more space at the bottom. What this means is that this perimeter equation can now be rewritten, and I don't need to have a B in it anymore. In place of my B, I'm going to put 1,800 over H. And then I have my plus H. And that completes guideline number 3 on the previous slide. I now have an equation where everything on the right-hand side has only one variable. Does that make sense? Okay. Now, step 4 talks about allowable values. So step 4 actually isn't even really calculus as well, but it leads into step 5, which definitely is where our calculus comes into play. We need to think about this problem in general. What are the restrictions? In particular, my restrictions need to be on the H, because H is what's left at this point in our equation. Had we done it and the restrictions, and we still had a B left in our equation instead, we would do restrictions for B. So taking a look at my image, what's the smallest thing, or I can't go any smaller than this value for h?
Well, 2b, right?
No, it needs to be a number. We're looking for a number here. Look at the image of what my shape is. What can h not be?
0.
It can't be 0 or negative, right? It can't be 0 or negative. So the first issue for h is that h has to be bigger than 0. Does that make sense? If h were 0, there would be no area, so I can't, there would be no fencing, right? I mean, like it wouldn't create an enclosure at all. So I need something that's bigger than 0. I can't have negatives, right? So that eliminates the negatives and the 0 at the same time. What's sort of an upper end on h? This isn't a hard, fast, exact value, but sort of an upper end that says, okay, well, it really can't go beyond this.
18,000.
1,800 seems like a really decent number. If you went a little bit bigger, that'd be okay too. But let's think what would happen if the area were 1,800. I mean, if the area is 1,800, but if the h here were 1,800, what would b have to be in order for this equation to work?
1.
B would have to be 1. That'd be a very funny looking fenced in area, right? It'd be 1 foot wide and 1,800 feet long. But it's at least an upper end that seems like I'm certainly not going to get anything bigger than that. Does that make sense? So this right here could be written instead like this. And that would take care of both pieces. I'm between 0 and 1,800. I don't need it to be any bigger than 1,800, and I'm not going to be able to get it for sure to be anything smaller than or equal to 0. Is that good for everyone? This gives us some constraints for what we're going to be doing. Now, the last step here, step 5, says use calculus. So this is the reminder, right, the hearkening back to stuff that we've done, a review, if you will, of what we did in chapter 3. We took derivatives, and we set them equal to 0, and we solved. Let me see if I have more space. I do. So my equation right here, I need to take a derivative of it. And if you would like, we're perfectly okay to multiply the 2 and the 1,800 before we start. So I will do that. This will be 3,600. And I'd kind of like to write this as h to the negative 1 because it's a little friendlier to take the derivative of. Okay, so I need the derivative of 3,600 h to the negative 1. Derivative, not antiderivative, derivative. What's the derivative of 3,600 h to the negative 1? Okay, negative 3,600, and then what? H to the negative second. Okay, does that look good to everybody? Okay, and at the end, what's the derivative of h? That's just 1. Okay, everybody good? All right, so we're wanting to set this equal to 0 or does not exist, right? The does not exist is really easy. The does not exist is when, well, let me rewrite it so you can see it best. If I rewrite this as over h squared, the does not exist is going to be at h equals 0, but we know h can't be 0 anyway, so I don't really have to worry about this one this time. It could have been an answer, but it wasn't for the particular context I have. But I need to solve this for 0. Okay, so this is algebra now at this point, right? It's a little bit messy algebra, but it's algebra. So we're going to move either of these pieces to the other side. I'll move the negative or the 1 over, so I have 3,600 over h squared equals negative 1. Yes?
0 just mean do not exist as well. It's not do not exist, it would just be 1. Right?
Say that again?
But you're saying the point where b do not exist would be if h is equal to 0.
Yeah, if h is equal to 0, my original equation would not exist.
Wouldn't that just be 1 though, because it's plus 1 in the equation?
Do you mean the solving that I'm working with right now?
I mean,
We're not going to get a 1 out of this. And it's not going to...
This negative, this is a negative power. So look at the h, which is like imaginary point on there, 0 on there, which is not.
So if I were to set this equal to does not exist, this will not exist at h equals 0. If h is going to be 0, I would get a 0 in the denominator, and this would not exist. Okay, Okay, so 0 is going to be the
Still
answer
have
from
the
this.
one there that's not under the fraction.
I agree, but I can't divide by 0. I mean, we could certainly merge them into a single fraction to see that, but it won't change the fact that letting it equal 0 as h is equal to 0 still creates a portion of my part that will not work. Yeah, okay. What would I do next from the negative 3600 over h squared equals negative 1? There's a couple options, I think. Yeah, that's a good option. We can multiply both sides by h squared. I like that one. Let's do that. So we're going to multiply both sides by h squared. So now I have negative 3600. That's it on the left. And on the right, I have negative h squared. All right, because these cancel. Now what?
Take the square root.
Yeah, I am going to take the square root. I probably need to recognize that it's negative on both sides. So I can multiply by a negative 1, or I can change both the signs at the same time, right? And then I would square root, yeah. So what is the square root of 3600? 60. Yeah, it's 60. And technically it's positive or negative 60. But I don't need the negative. Why?
Because it's greater than square root.
Yeah, because I established down here that h can't be negative. This is a good reason for why we needed to do this. There's going to be a problem we're going to do later that's going to allow some negatives. So we do have to think about that option when we take square roots. On this one, I don't need it. So I only end up with h is 60. Okay, so 60 should be my optimal value, but I have to show that it really is. In particular, I want my perimeter to be a minimum. And I need to show that if we're at 60, I didn't create inadvertently a maximum. Because I could have, because the process is the same to find maximums and minimums. So the way that I can do that, at least one of the ways, the way that we were most comfortable, I would think, with, is a sign chart. Now, our sign chart has a maximum and a minimum. It goes from 0 to 1800. We know that because those were the values that we established on the previous slide, right? And I don't really care about whether or not 60 is halfway in between. I know it's not. It's just between. It's good enough, right? My sign chart means I'm going to test values in each of these areas and see what happens in the derivative. Okay? So somebody tell me a number between 0 and 60 that would be nice to work with. 1 is fantastic. And now I need a number between 60 and 1800. 100. Okay. And remember, it doesn't matter what you pick. As long as you pick something between, you're going to get the same answer that I will if I pick these, okay? And we're going to put these red values into the perimeter prime, right? Or this version of it if you prefer. So we're going to take each one of these values and we're going to put it into the negative 3600 over h squared plus 1. And our question is whether or not we would get a positive or negative, okay? So if I put in the number 1 into this, what am I going to get?
Negative 35.
Yeah, it's negative, right? And you get something here. If I put the number 1 in here, I get negative 3600 plus 1. That's a big negative number. What if I put the number 100 in?
0.6.
It's positive. So what did the negative and the positive tell us? Well, they told us the direction of the graph. Negative means it's going downhill. Positive means it's going uphill. So what happens, hang on, different class. What happened right here? It's a minimum, right? I'm going downhill and I'm going uphill. This one has to be a minimum. What were we looking for, max or min? We were looking for a minimum. So we found it. And we need to make sure, we've done all the work, we just need to make sure we answer the question that was asked. What is the question that was asked? Find the minimum perimeter. Have I done that yet? No, I have not. What have I found?
So minimum height.
I have found the minimum height, correct? So I have found this height right here, and what did I find it to be? 60. Okay, so I'm going to mark it on my graph. This one's 60 now. So how can I find the two bases so that I can find my perimeter? Put it back in where, Andrew? Into the area, right? This one right here will work really nicely, correct? This is a relationship between B and H, where that's the only two values in it. So if I put 60 in for H, what's 1800 divided by 60?
30.
Yeah, so 1800 divided by 60 is going to be my base. My base ends up being 30. So I have either from an image standpoint, 30, 30 here, and I can just add them up. Or I can put them back into this formula if you prefer, 2 times the base plus the height. That's fine too. What's the perimeter? How much feet of fencing do I need? 120, right? I need 30 on the top, 60 on the side, 30 on the bottom. I need 120 feet of fencing. So the perimeter, right, is 120 feet. It's important to answer the question that's asked, especially in WebAssign, because it's just going to tell you you're wrong. It doesn't always tell you exactly why. It could have just as easily asked you to find the minimum perimeter, right? It could have asked you at the very end here to tell you the course, find the minimum perimeter, and instead of saying, it says, and the dimensions of this too. We found the minimum perimeter in the dimensions. We also need to do dimensions. It would have 2 blanks. So the dimensions we already found, we just didn't write it down. The dimensions are a 30 by 60, right? So that's a secondary question that's asked on this one. So the dimensions are 30 feet by 60 feet. And sometimes it'll only ask one of the 2. I'd forgotten that it asked both. I didn't look at it carefully. Okay, what do you think? Andrew?
For finding if it's a minimum, can you not also just do the second derivative and see if it's...
Yes.
Okay.
You could. That would be another option. And so Andrew's remembering the second derivative test. So the second derivative test says that if I were to take the second derivative of this and I were to plug 60n, if I got a positive, it would be concave up and it would be a minimum. And if I got a negative, it would be concave down and it would be a maximum. That is the other option instead of a sign chart. WebAssign's not going to be able to see that you did a sign chart. Y'all know that, right? That's something that you need to do anyway, because you need to verify that you're finding what you think you're finding. So that's something that's just on you. But in terms of like written work, quiz, and exam, all of those, I will be looking for either the sign chart or you can do the second derivative test just the same. Yeah. You have to verify that you really found a minimum or a maximum if that's what your problem asked for. Good? Okay, let's try another one. This is, both of these, the first one and the second one, are like stereotypical. If I didn't teach them in calculus, it would be like a sad day because they show up in every single calculus book. You're never going to see a calculus book that's not going to have these 2 examples. And I don't mean this exact one. It could have been a rectangle that was, not along a river or something. But you're always going to have something where you're doing a rectangle and you're doing something with this one, which is a box with a top or no top. All right, so imagine here. This one says you have a box with no top that's being built by a 6-foot by 10-foot sheet of cardboard. You cut a corner out of each of the corners, like you cut a square out of each of the corners, and you fold the box up. So the picture you should have in your mind is like a shoebox. Okay, so imagine having just half of the shoebox, not the top and the bottom, just half of it, okay? And you cut along the edges, right, the corners of your shoebox, and you laid it flat. And if you did that, your picture would look something like this. And it would have these missing little corners right here. That's not good. Let's try that again. Hang on. Okay, so I'm going to take this image and I'm actually going to show you a little bit more closely what it actually looks like. This picture that's drawn right here is what we're going to need to use, but let me actually show you what the image would look like if you did what I suggested. Whoa, that's not what I meant to do. Let's try it again. And there would be these fold marks, and the folds would look something like this. I'll put them in dotted for the fold marks. There would be this folded piece that would have come from here and here and here and here, and now they're folded flat. Can you picture it? Like physical box. I should really bring a box in when I do this example. We should cut it apart and you should see it. Can you picture what that would look like? It would look roughly speaking like this. Now, the image that I have drawn over here on the left is sufficient enough without me actually doing the erasing And so we'll go with this image over here and put my dotted lines in as well. Now, it tells us, so this is my picture, right? Step 1, if you will, or guideline 1. It tells us what the length and the width are of the box to start with. Now, simply because I drew it as a long rectangle, I'll put the 6 on the top. And I'll put the 10 on the right or left, either way. Okay, so that's the actual piece of cardboard that we're starting with. And we're going to take a pair of scissors and we're going to cut these little squares out of the corners. And then we're going to fold it along the dotted lines. Okay, everybody good so far? Excellent. And it tells you that the cuts along the corners are X inch squares. So it means that we've got an X here and an X here. And that's true for all of them. I'll draw them all in, but you just certainly don't have to list all of them. They're all the same sized boxes that we're cutting out of the corners. Okay, everybody good? Okay. Now when I fold the box up, it's going to have a third dimension. Right now, it has length, it has width, it has area. But if I fold it, it has the dimension that's the third dimension, which is called what? I'm going to have height. I'm going to have one more thing, like the three-dimensional dimension. The word I'm looking for is volume. I'm going to have volume. Right? If I fold it up, it's going to actually hold something, so that's going to be volume. Two-dimensional object doesn't have any volume, but if I fold it up, I'm going to have a three-dimensional object and it would have volume. Everybody good with that? Okay. So I'm trying to find the maximum volume, and here it is in the directions too. I want to find the volume. So generally speaking, do you remember the formula for volume of a rectangular solid? Because that's what this is going to look like. It's going to look like a rectangle that's three-dimensional. Let's do this. What's the area of a two-dimensional shape like this? Base times height or length times width, right? Okay, so I'm going to use your length and width as the descriptions because what happens when I have volume is that when I fold these little edges up now, I actually end up with a third dimension of height. So the volume of a rectangular solid is length times width times height. Now, one of these dimensions is pretty straightforward from my picture. It's the height. If I fold my box up along each of those dotted lines, what's the height of the remaining box that I have, the three-dimensional box? X. Does everybody see that? If I fold it up, all of these sort of sides kind of come out of the board. So this piece right here, when I'm folding, flips out here, and it's going to have a height that's the same as the corner that I cut. So it's going to have a height of X. Where'd it go? Thank you. Okay, so my height here is X. The length and the width are a little trickier. They should be related to the 6 and the 10, right? But they're not 6 and 10. Why are they not 6? Let's just do a 6. Why isn't the width 6? It's 6 minus something. I've cut corners out, but it's not quite 6 minus X. It's 6 minus 2X because I've cut out 2 corners. Okay, are you seeing that? So I had this length of 6 here, right here, and then I cut out this piece and this piece. So my length, or my width, whichever one you want to call it, and I'll need more space here now, is going to be 6 minus 2X. What would the other one be? 10 minus 2X. Okay, everybody good? Okay, the nice thing on this particular one is changing all the variables into a single variable, namely X, was pretty straightforward within the process of what we were doing. Okay, so at this point, we're at the end of step 3 of the guidelines. We have a single equation with one variable. And the volume is what we're trying to maximize in this case. So we know what we're trying to maximize. There's only one equation that we even have to work with, so we don't have to sort of figure that piece out. All right. However, as we take a look at this, what I want you to recognize is that there are some restrictions on what x can be. What's the lower end restriction? It can't be negative. So, and it can't be 0 either, or I wouldn't have any volume, right? So 0 is my low end. What's the high end value?
6.
Smaller than 6. But you're thinking along the right lines.
That'd be 3.
It'd be 3. Where'd you get 3?
Because it's 2x.
Yeah. Whatever you're cutting off of, we're doing the 6 because it's a smaller number, by the way, okay? So whatever we're cutting off over here, we have to cut off over here. And the most that I could cut off is half of the length in total. And if I did, I wouldn't have a box either. So 3 is my upper end of my restriction here. Does everybody see why it's 3? Yeah? Okay, cool. All right, so we are ready to do some calculus, but I would encourage before we do the calculus to multiply this out because the derivative is going to be easier if I change this equation into something that's a little bit friendlier and not have to use chain rules and product rules and such like that, right? Product rules specifically on this one. So we will multiply this out. So this is 6 times 10 is 60. 6 times 2x would be negative 12x. Negative 2x times 10 is negative 20x. 2x times 2x is positive 4x squared. All that's going to be multiplied by x. And combining the terms. Oops, I left off my x. That was negative 20x there in the middle. I'm sorry, yeah, that one. All right, so if I distribute, I will have 60x. I can combine these two, so that's negative 32x squared, and then positive 4x cubed. Is everybody good with that? All right, let's take a derivative then. Nice polynomial form. What's the derivative of 60x? Okay, the derivative of negative 32x squared. Negative 64x, and then, what about the 4x here? 12x squared, very good. All right, optimization. Right now we're trying to find an extreme value, right? We're trying to find the maximum in this case. What do I do as my next step after I've taken the derivative? Right, I want to set it equal to 0 and solve. Now, this one is not super friendly, and the reason is because it's a quadratic form, which means that our default is to try and factor it, and it's not going to factor. Okay? It's just not. If it factors, we're definitely going to go the factoring route, but this one's not. I'm just going to cut to the chase and tell you without letting you try it. We don't have time for trying. But it's not. Now, we could at least make it a little bit smaller. We could recognize that 60 and 64 and 12 all divide by a common factor of what? They don't divide by 12. They don't divide by 6. 4 will work, though. I could divide them all by 4. And I'm going to turn it around when I do that. So I'm going to divide each of them by 4 and move the x squared to the beginning. So this will be 3x squared minus 16x and plus 15. So if I can't factor this, what options do I have next? There's really 2 options that we have. Quadratic formula is the one that we're going to use. The other one that you're probably not going to choose anyway, but you could, is completing the square. Completing the square is the other option you have. We're going to do the quadratic formula. So we have this equation in the quadratic formula. So the quadratic formula is x equals negative b plus or minus the radical of b squared minus 4ac over 2a. And identification purposes, this one's a, b, and c. And make sure that this b is associated with the negative 16, not just 16. So at the beginning, if I have negative b and b is negative 16, I'm going to have a positive 16. And then I have negative 16 squared minus 4 times a is 3 and c is 15. All over 2 times 3. Your calculator will work through that just fine, and it will give you 2 values. Why is it going to give you 2 values if you do this correctly? There's a plus or a minus. Okay, so I'm going to do the 2 values. to sort of give us a go at what we're looking at here and to show you why the last step of identifying from 0 to 3 was so necessary. These are the two values that it gives us. 4.12 and 1.21. One of those is not possible. The 4. I can't cut 4 inches off of a side, right? I only have 6 inches on one of the sides. So even though 4.12 is a viable answer, and it's the one we would have gotten if we did addition, by the way, it can't be the answer for our problem. It doesn't make sense in the context. Okay? So either going to a second derivative like Andrew suggested, or you can go back to a sign chart. I'm going to do a sign chart. We have the lower end is 0, we have an upper end is 3, and we have the point of question, which is 1.21, and we want to make sure that we're going to get the maximum at that point. So what's a number I can test before 1.21? 1. And after 1.21? 2. Those would be fabulous. And where am I testing them into? It's the derivative. And you're welcome to put them into the derivative that we had up here, where we had divided by 4. That's okay as well. It would be a little bit smaller numbers. It doesn't really matter, but it would work. And if you put these in, you're going to get a positive when you put in 1 and a negative when you put in 2. What does positive mean? It's going up. And negative means it's going down, which gives us a maximum. What were we wanting, max or min? A maximum. So we did, in fact, find a maximum by doing this. What does it ask us to find? Find the value of x that maximizes the volume of the box. Have we found that? We did on this one. The answer we have right now is, in fact, our answer. It's 1.21 something. What? Inches. Those double lines right next to the 6 and the 10, if that's not familiar to you or at least super, that's inches. Okay, so you can either use that notation in terms of writing it down, or even better, write in words. This is inches. No, they still could have asked you other things, right? They could have asked you, find the perimeter of the bottom part of the box, right? They could have asked a different question, but they didn't. All right, I'm going to stop the video right here. I'm going to post a video for number 3. We have time to start it, but we do not have time to finish it. It would make it more sense if you did it all at one time. So I'm going to do it that way. Sound good? All right.